that, Lars, why don't you take things away?
Yeah, thank you, Bob. So my talk is about a new training module that we are developing for code performance and scaling. The purpose of the talk is to help users writing a better proposal. But the purpose for today's talk is to get everybody on the same page and to make everybody aware that there's a new resource, you know, this talk, the slides, or when we give that talk later on this year a couple of times. So it's a slightly modified version of the talk. Last time I gave it together with Kenneth, and of course he spent 7-8 minutes on what is exceed, and of course we are going to skip that. And then also in my talk, because we have only half an hour, I will go a little bit faster than we usually go. So so I usually start at this slide number 8, that to make users aware that a well-justified computational plan, that's the backbone of a good XRAC proposal. Science is important, of course, but the reviewers will focus on the computational plan. For funded projects, technically the science is not even really reviewed. However, the science, the computations that are proposed in the proposal have to match the science. So it's not that the science is completely off the table, but it's kind of the framework. It sets the stage. What the proposal is about is demonstrating competent use of the expensive resources, all the resources that are provided by Exceed. And I'm going to delve into the components of what is a well-justified computational plan in a minute. For now, the hands-on advice is, it is not your NSF proposal, your successful NSF proposal, and then 2 sentences saying, now I want 2 million SUs. That will not, that is not a good proposal and will be most likely will not succeed. I will talk about a lot of data that you have to produce to make your proposal a good proposal. And if you don't have allocations right now, you can always get a startup. You can submit a startup at any time. It's quick turnaround. The entry level, the hurdle, the entry bar is really very low. 4 or 5, oh man, it's paragraphs. I think that should be sentences. 4 or 5 sentences detailing the field of science, your work, what you want to do. And relevant in this context is to prepare a full proposal, but it can be anything from developing code, experimenting, and so on and so on. You get some generous amount, and GPUs are also available, and there are specialized systems for Hadoop style research and artificial intelligence and so on. So once you have a startup, once you can run on the resources that you are targeting, you now scale up to a full proposal. And my talk is full of advice where I say not everything in the talk will apply to every proposal, and you just have to apply some common sense. And one common sense fact is that requests from new groups are under more scrutiny than proposals from well-established groups. Also, well-established groups have a better chance of winning very large awards, and a new PI should have established a track record first. Also, common sense is that you compare your request size to the total availability of the resource. There's really no secret in how big a system is, and you have the number of hours in a year, and so you can calculate how many service units are being provided by a resource, and you have to limit yourself to a reasonable fraction of the target system. Reasonable is, of course, that is a wide range of what that can mean. And of course, smaller requests face less scrutiny than larger ones. Another piece of advice is focus on what you really need. only one resource, or if you meet multiple, there has to be a good reason. What are not good reasons is it is convenient, or if the system is down for half a day, can I then use a different system? Those are not good reasons. So hands-on advice, use common sense when preparing your proposal, pick a reasonable request size, internalize that there is fierce competition for these resources. These resources are highly sought after. They provide a really excellent, they're an excellent resource for all kinds of science. Therefore, there are always a lot of proposals being submitted. There's a real competition. And that also means that overly ambitious proposals do not fare well. Ambitions could be generally too large, or where reviewers are not, where you cannot convince reviewers that all the computations that you propose are really actually needed, and so on. And we will go into some details in a minute. So what makes a good proposal? A good proposal that puts you in a position where you can compete with many, many other groups. The basic outline is description of the science, you detail the specific scientific questions, and you describe the software, how it is parallelized, and so on. And then the key part of your XRAC proposal is a computational plan, and from that, a realistic and accurate estimate of the service units that you would need for the calculations that you need to answer your scientific questions. And for that, to make the computational plan and the estimate, you will provide a lot of supporting data like scaling and computational efficiency, and we will talk about that for the rest of the talk. So the proposal is somewhat comparable to your NSF proposal, but with a completely different focus, now mainly on the computational plan. And you have to keep in mind that the reviewers are not necessarily domain experts. The review panel covers basically all areas of science, but for a given proposal, it is not guaranteed that all your reviewers are domain experts. So you have to find a broader approach to explain what you are doing. It's important that you connect your scientific question to the computations that you are proposing. What equations are being solved, what algorithm is applied. Also, reviewers want to know how the code is parallelized, things you did in the past to understand what the performance is, how did you increase performance if that is applicable. You do all that to assure reviewers that you know how to run the code, and more specifically that you know how to run the code on the target system where you want to run later on. And your computational plan has to have a lot of details, like the number of calculations you want to do and how long every calculation is, how many nodes you will use, and then how that relates all to your scaling data. Reviewers, I have been a long-time reviewer. I always like to do some basic math to follow what is in the proposal, so make that easy for the reviewer, so that there can be a verification of your SU estimate. And the scaling data that you will provide will also convince, hopefully, the reviewers that you know how to efficiently use the resource. And so for an individual calculation, you create something like scaling efficiency, and from there you get total runtime, and so on, and details are to follow. And reviewers will be really appreciative of all the efforts you document, particularly when you present them in a very organized fashion. So I guess everybody has reviewed proposals him or herself before. The easier you make it for the reviewer, the better is the chance, the higher is the chance that you are successful. So the computational plan takes center stage again, and therefore we request X million SUs on the resource will not get you anywhere. The reviewers want to be assured that you know what you are doing. Now, what in an ideal world, in an ideal scenario, the reviewers would judge and investigate the efficiency of an application. But that is, of course, very hard to do and cannot be done within the review process. So one of the things how the review process is set up is that the review panel will use scaling efficiency as a proxy for overall efficiency. And then scaling efficiency or scaling plots are also used for other things. But that is one of the main things that reviewers look at to get proper scaling data, and they will use that as to understand if the efficiency of the application is reasonable or not. And then particularly, these are large and expensive resources, so the reviewers like to see scaling on the target system or on a similar exceed system. And of course, for smaller requests, that is less stringent than for larger requests. Again, common sense, you have to apply that. So you present scaling for a typical case or for typical cases. You present timings for a few time steps or timings for a smaller sample. Of course, not all setups are easy. If you do AMR, you choose a simplified setup and discuss implications. And then you should document scaling that covers the number of nodes that you target for production or apply some well-justified extrapolation from smaller sample cases. And also your scaling data should target a node count for production. From the scaling plot, you will then pick a node count for your production calculation. And that target node count, that should be where the scaling is good. And I have a few slides on that. And the other thing you have to do is you have to balance wall clock time and scaling or parallel efficiency. I think that becomes obvious in a few minutes. So let's first talk about speed up and parallel efficiency. First, I go into details for strong scaling. And in strong scaling, the workload is constant, even as more and more resources are applied. You apply more and more cores or more and more nodes. Ideally, of course, execution time decreases with the number of resources. And you derive a speed up by creating or calculating the ratio of execution times, the time on one node, the time on two nodes, time on four nodes, or 1 core, 2 cores, 4 cores. And what you have to do is you use T1 over Tn. So in that setup, your ideal strong scaling is linear, and hence the efficiency of the quality of the scaling is easy to assess. If you do it the other way around, you plot time on n resources over the time on one resource, then your scaling is not linear, but 1 over x, and that makes things much, much more complicated. So pick something, in any case, whatever you do, pick something where the ideal scaling, the ideal speed up, or the ideal parallel efficiency is a linear relationship. Of course, when you do strong scaling experiments, and also for weak experiments on a single node, you will always see that the scaling is not ideal, because on a single node, you will run out of memory bandwidth before utilizing all cores of a node. So reviewers, of course, know that. You just have to discuss it in your proposal a little bit. Often, I would say strong scaling experiments are often conducted for smaller calculations and often on a single node. On next slide, I have an example how that would look like. X-axis is cores over nodes, cores or nodes, and Y-axis is the speed up. A strong scaling, the amount of work is fixed. And yes, I choose a setup where the ideal scaling is just a linear relationship. And in orange, you can see what the measured speed up is. And of course, anything where your performance drops, that's out of the question. I think that is obvious. But what is not obvious to everybody is that you should, or yet that you must not pick just maximum speed where the wall clock is shortest, because at that point, the efficiency is already very low. I mean, if you go now from where the arrow is to the left, you can basically save as use for and trading that for just a little bit of increased wall clock time. So you pick from this graph, you pick your node count, either where your scaling is good or where your scaling is reasonable. And the more you go to the right, the more you have to argue why that is actually necessary in your code, in your case. And I will come back to that point later. Just a little slide. Why is it difficult to assess speed up when you do 1 over x? I mean, on the left diagram, that's pretty easy to see how far you are away from ideal scaling. On the right, that is much, much more difficult. And if reviewers find that it is too much effort to make sense of your data and they cannot put all the puzzle pieces together, or even more severe, if reviewers become suspicious that there may be something hidden that they don't understand and they have the suspicion that the numbers are inflated, then they may severely cut your proposal or even reject it, and then you have to wait and redo the whole thing. So it's always important to make the job easy. Now, speed up and parallel efficiency. Now we talk about weak scaling, where parallel efficiency is takes center stage. Now the workload is proportional to the amount of, oops, the sentence is screwed up. The workload is proportional to the amount of resources that are applied. Ideally, now the execution time stays constant with the number of resources. Resources, again, either cores or nodes. So now the parallel efficiency is defined as the ratio of execution times. And if you plot something that is T1 over Tn, that is the time it takes on one resource over the time it takes on n resources, then the ideal parallel efficiency is 1, so your timing didn't go up. And if your timing has increased, then your parallel efficiency is lower than 1. And here you may use a linear log scale for the x-axis. It depends on what range of how many, sometimes a decade, you cover a wide range of node counts. It's often conducted for larger calculations on multiple nodes. And also keep in mind that in some fields, it's more common to use progress rather than execution time, like time steps per hour, or time steps per SU, or in molecular dynamics, simulation time per second, things like that. My personal view is this is all fine, but do not confuse reviewers. If you make it too complicated, and if you do not give a brief explanation, you know, the one sentence, what that unit means, if you don't make that accessible to non-domain experts, then yeah, you make the life for the reviewer harder, and that will all count against you. Okay, so a typical scaling plot looks like this. You have the number of nodes, x-axis, you have parallel efficiency. Your ideal parallel efficiency is 1, and then at some point you scale beyond the point where it is then reasonable scaling and then bad scaling. So parallel efficiency is ideal time over actual time. And the ideal time is the time it takes on the smallest number of nodes where you can run your experiment. So if you target 1,000 nodes, you're not required to start with 1 node and then go to 10 and then to 100. You will start with a reasonable number of nodes. Usually memory concerns, memory consumption is a concern there. And then you cover some space in a number of nodes and create a plot. And again, as in strong scaling, you then pick the number of nodes for your calculation. Hands-on advice. When picking a target node count, you have to be reasonable there, particularly for large calculations with a high SU consumption. Do not target quick completion at the expense of efficiency. The goal always is to demonstrate that you know how to use the resource, that you know how to use it efficiently, and that will then convince the panel to give you a good review. The review panel is not overly concerned with wall clock time. The award period is a full year, and you're expected to run through the whole year. That fluctuates, of course, wildly, and if you have only a small amount of SUs, then you should be able to run it just to consume the SUs in a short amount of time. But for the really large proposals, at some point you will be running constantly. You will have a constant burn rate through the year. Yeah, more advice. You balance efficiency and runtime. When you're in doubt, stay on the efficient side of things. Do not push for early completion at the expense of efficiency. If you're running multiple calculations, if you're planning to run multiple calculations that can run independently, then of course you can reduce wall clock time by running multiple or advancing multiple calculations by submitting multiple jobs. If you have a really very long calculation, then you also have to consider the time in the queue. So as a rule of thumb, maybe for every 24 hours that you are running a reasonably large job, you will spend 24 to 48 hours in a queue. So if you have a proposal, if you're proposing a calculation that will take, in an uninterrupted ideal scenario, 9 months, then the review panel will tell you that you will not be able to continue to finish that within a year because your jobs will be queued at some point. There are a little bit of special considerations for time-critical projects, but only very few fall into that category. The most prominent one is probably severe weather forecast. Now you can push a little bit farther and go a little bit further to the inefficient side of things. But in the end, if you're asking for 2 times as many resources just to reduce your wall clock time by 20%, I don't think that is a winning proposition as well. If you push too far into inefficient territory, you will be told to optimize your application and you may receive a severely reduced allocation. If you have small calculations, and then naturally a lot of them, I mean, if you have only small calculations and a few, then that doesn't amount to an XRAC proposal. So let's assume you have small calculations, but many of them, then devise a strategy and explain how you will bundle multiple calculations on a single node. Exceed resources, you often don't do node sharing, so that's up to you to do that. And also investigate and present the most efficient setup. How many of your calculations do you have on a node, and how far do you scale, if applicable, every single of these calculations. Okay, so we have covered now scaling. Now you use the same data to estimate the number of SUs. From your scaling plot, you know how fast your code is or your application is, and you now have determined how many nodes or cores or resources you want to use to do your production runs. And now from that number of nodes and from the speed of your application, you now can do some simple math to estimate the total size of the request. So the scaling is not just to convince efficient use of resources, it also enables you to give an accurate estimate of how many SUs you will need. So you extrapolate from a towards the total number of time steps or the resolution that you want, and so on and so on. Always present details for all planned experiments. Allow the reviewer to easily follow your estimate. Give the reviewers reassurance that your estimate is not, or estimates are not bloated. And as a reviewer, I always like it if there's a table that will summarize the individual experiments, particularly when you have a large group, and then there are lots of experiments, there has to be something. Parameter studies highlight that you are really selecting a reasonable number of combinations, and how did you come to that conclusion? Also, there are little things, don't forget to justify storage and such. Here's an example that I made up. So the simple math is number of nodes times total run times number of simulations. That is the SUs. You use the scaling to justify the number of nodes. For scaling and performance, you translate simulation time into total run time, and your resolution and the simulation time, that is justified in the proposal. That's from the sciencey bits. So here I made up some examples. You can look at that a little bit later. For community codes and well-known codes, you still have to do these scaling plots. It's not enough to refer to some other document. Reviewers want to know the scaling on the target machine and an accurate estimate of the SUs. Some more considerations: add storage, add special queuing demands, disclose any problems that you anticipate. Nobody will ding you for that. Resource providers are happy to work with you, and they are happy to know beforehand if you anticipate problems. Our big advice here, I think that goes a long way. If you have done anything to improve or understand the performance of your code, write about it. Reviewers like to read what you did, and that assures them that you know what you're doing. I'm speeding up here a little bit. We're a little bit late already. So summary is, design your proposal around the computational plan. Use scaling as a proxy to demonstrate efficient use. Use that also to detail basic math for your SU request. Be reasonable, ramp up over time. It's a tough competition, but a little bit of effort goes a long way. These resources are very valuable, and you will be very happy using them. Okay, I'm done. Questions?
Great, thank you, Lars. That was fantastic. Do we have any questions? All right, if not, I'll just make a quick comment and say, first of all, thank you for doing this. This is something that we should have done years ago. Also, though, you did mention on one of your slides that often nodes are not shared and you should bundle your calculations. Definitely good advice, but everyone keep in mind that we do have a few XC resources that do have shared nodes. For example, like Comet. That's
why I say often.
Yeah.
I mean, I'm preparing the users for the worst case scenario. If they are, you know, if their calculations are not big enough for a single node. If they will find out that.
But excellent advice, because in the past, I can remember many times when somebody would be running like a single core job and using a node. So fantastic. Last chance, any questions before we go? All right, and there was just a comment from Paul Rodriguez. He said, I think also software tools, programming environment being used are useful to know. That was a comment from early in the presentation.
Yeah, maybe I can add that to one of the slides. It's basically everything that you know or understand will make an impression on the reviewers towards, hey, that user knows what he or she is doing.
Yeah. All right, well, thank you, Lars. Go ahead and stop sharing, and we will hand things over to Kenneth Yoshimoto. And Kenneth, I know we're starting a few minutes past 10:30, so we'll let you go over a minute or two. Yep, so go ahead, Kenneth, whenever you're ready.
Okay, can you hear me okay?
Yep, audio sounds great.
All right, and you can see the slide?
Yes.
All right, so my name is Kenneth Yoshimoto. I'm in the applications group at San Diego Supercomputer Center. My educational background is actually molecular biology, wet lab viral gene expression, but I've been doing computer stuff for quite a while, and how long I've been doing that sort of thing will be horribly apparent about halfway through this talk. So be prepared. So today I'm going to talk about gateway production monitoring. I am working on a project called the Neuroscience Gateway. Let's see what's going on here. Okay, so I'm going to talk about two gateway production monitoring scripts that I've written that exercise the REST interface and then the browser interface of a gateway, a science gateway called Neuroscience Gateway. So the Neuroscience Gateway does computational neuroscience research. It's based on the web app code from something called Workbench Framework. And this is code that was originally used in the CIPRES Science Gateway, still used in that gateway, and you can find that at philo.org. In addition to Neuroscience Gateway, this code base is also used in the COSMIC2 Gateway, which is a cryo-EM data processing gateway. So this application can provide both a non-API web browser interface, so basically just web pages to do its thing. And it can also provide a RESTful API where the interaction with the gateway is very well defined. NSG makes both of these interfaces available to users. So as I said, I wanted to do routine monitoring of our production status. So I wrote some programs to do a once-a-day test of both of those interfaces. So what's the motivation for this? Well, we would occasionally get reports from users saying, hey, I can't connect to your gateway. Is anything going on? And then we look, and sure enough, some aspect of the gateway is down or not working. And that's the most horrible thing, to have your end users report failures to you. We want to catch those before, ideally before any users notice them. So we definitely need some production monitoring. So the way I think about it, there's two ways to do production monitoring. And the first is sort of an alert on failure mode, where you try to list everything that you can think of that can go wrong with the gateway, and then write tests that get run very often to alert you to when something is not right. And there are advantages to that. You can run them very frequently because you're only alerting the humans when there's something wrong. And you can run them on the web server itself. It's easy to probe different aspects of the system from the web server. The alternative way to look at it is send a confirmation when everything is good end to end. And I sort of like that style of thing a little better. The disadvantage to it is that you don't want to run it every 10 minutes or so, because you're just going to spam the humans with yes, I'm up, yes, I'm up, yes, I'm up messages. But the thing I do like about it is that it can catch parts of the system that fail that you didn't really consider. So I prefer to do the end-to-end confirm good testing. And then why does NSG provide two interfaces? Well, we started with the web browser interface because that's pretty familiar to most people to go through web pages, fill out forms, be guided for what you're supposed to put into each field in a form. So it seems a little more comfortable to people to use. So that's the first thing that came up. And we also provide a REST interface because there are other communities that want to use NSG as a back-end processing resource for the computation they want to do. So they need a programmatic method to send us work and then retrieve output back to them. So we've got both of those. Now, I remember one conversation I had with my partners on the project, and I was telling them, why don't we just give these users curl commands and maybe a Python notebook, and then we can totally shut down the web browser interface. Well, that didn't fly with them. So we've got both of those interfaces usable by the user, so we need to monitor both of them. So I'm going to talk about the REST interface testing first. So curl is a sort of a web client. Equivalent other programs can be used to interact with the REST interface. I used curl in my testing. And the way users can interact with the REST interface is documented. And it's a pretty simple workflow. So we use a one-shot curl command to specify the input file, which is a zip file containing code and input data. And on that same curl command, we're going to specify job parameters, and then we're going to submit the job. And that's a one-shot. Then after we submit the job, we want to query job state to see when it's been submitted and when it's been completed. And then we're going to want to retrieve and verify the output. So not too bad there. So the prerequisites to using the REST interface are that the user must have an approved NSG account, and they must generate an app key in order to provide that to the curl command. So here is the curl command. It's basically a post method form that gets filled out. The config file is the username and password, so you don't have to put that in the command line. You provide the app key that was generated previously, and you connect to the NSG REST server, and you provide different parameters for this run of the job. So the tool is the backend application framework that we want to run for this test. And there are a number of other different job parameters, like a number of cores, number of nodes, what the runtime is, the program file name. So the program file name is what user provided program we want to run in that tool framework. So NSG allows users to submit executable code to be run on Comet or our other systems. So we also provide command line options. And then this last thing, input file, is the zip file, path to the zip file on the local system that contains the executable code and the input data. So the curl command knows how to present the username and password, and how to fill out the form, and how to upload that zip file to the REST service. So one shot and your job is submitted. So this is the response from that, that curl command. So it's structured, it's XML. So there are tools for just about any language to parse information out of there. And the important thing you'll see here is the URL for referring back to that job. We can query this URL for information about this specific job that we've just submitted. So we want to query the job status, and here's the curl command to do that. Pretty simple. We just provide the username and password and the app key again, and get information from that URL. So the response is in the job stage field. We see that here are the job stages submitted. So we know that we did a successful submit. And at this point, we can send out email, the confirm good email to all of the notification emails in our list and say, yeah, for today, this morning, the REST interface was able to handle a successful job submit. So then, because of the batch system, there's going to be a delay between when we submit the job and when we can verify the output. So we need to store some of the job information for that later output verification. And the two things that we're going to store are the job URL and information about the expected output file. And here's what that stored structure looks like. So you don't have to worry about parsing exactly what this surrounding code is. Just note that there's a job URL stored in here, and that there's a file name at the bottom of this screen. There's something called mu_output.dat, and that's going to be extracted out from the output zip file that we download. And this next line, the results file, is a path to our reference output file. So those two things, the thing we extract from the job we've just run, and this reference output file that we've saved on our testing system, the file compare should be exact. And if it's not, then something we don't understand went wrong, and we need to go check that out. So these are the steps for checking the output from the REST interface. So we're going to look at all the jobs whose information we stored. We're going to query the REST interface until we find completed jobs. Then for any of these completed jobs, we're going to download that output.tar.gz file, which is how NSG packages its outputs. We're going to extract that mu_output.dat, the expected output file, and then we're going to compare it with the reference output file. At that point, we can give a thumbs up, thumbs down, whether that output verification worked, and we'll send out an email to people on what happened. And then we're going to do some cleanup. We need to remove our working directory where we did the extraction and comparison. And that's basically it. So monitoring through the REST interfaces, not too bad. That's what it's for. It's meant for programs to interact with it. All right, now let's take a look at the browser interface. So, this is how a lot of users use NSG through a web browser. This is the flow of how a job is submitted. Now, the thing that's different about this is that there's a two-step process for uploading the zip archive that is used for input data. The user is expected to use the browser to upload that data as one step. And then the second step would be to create a task, as we call it, for submitting the job. And then that task for submitting a job will need to reference that input data. So basically 2 different steps for uploading your input and for submitting your job. And then the other steps are the same as for the REST interface. You're going to need to query job state and then retrieve and verify output. So things to worry about for the web browser interface that we didn't really need to worry about with the REST interface. Cookies. So cookies are used to maintain state for the session. And we did not need to worry about these for the REST interface. So curl has a facility for saving the cookies that are presented to it during an interaction. So we're able to save those cookies, and they call it a cookie jar, and then specify that these be used in subsequent interactions with whatever web server it's talking to. There are also tokens that are sent back in the output or the response text from the web server. And these are to maintain state through a chain of interactions. Like when you're creating a job, you need to do several steps in order to create that job. And these tokens are, this token is, you need to save it and then present it out to the next step in that chain. So data IDs and task IDs are the unique identifiers for those items in the NSG web server. And so when we select a data ID or a task, or when we want to select a data item or a task item, we need to be able to find the ID that's associated with this test. So what we're going to have to do is generate a predetermined label, generate a unique label that we can tie to a data item or a task item when we create it, so that we can refer back to it in the future. And again, this wasn't necessary for the REST interface because it gave us a unique URL to reference our job. So the prerequisite, we don't need an app key as we did for the REST interface. All you need to do is have a username and password for your NSG account. Okay, so let's go to a matter of style. So as I said, I've been doing computer stuff for a long time. My first web programming I did back in the mid-90s. So that's a long time ago. And I'm definitely still stuck in that mode of programming. So I am not really up to date on the latest web technologies and frameworks where people use the web to do a whole bunch of neat stuff. So here is a production web form that I wrote. This is the Lynx browser running in a terminal. And you can see it's a 3-field form with a submit button, essentially. So let me show you the source code, the page source for this. So it's really simple. It's HTML, nothing at all in the head. And the body is just a post method form with 3 fields and a submit button. So not much to it at all, really. So that's my style of web programming. I preferred if everything were really simple like this, no fluff. I don't like any fluff in my web programming stuff. So let's contrast this with the NSG Portal web browser login page. I couldn't even fit this in the screenshot I captured. You notice that there are tabs at the top going across the top doing different things. There's a sidebar. There's a footer I did not capture. Basically, this is a 2-input post form. And let's start going through the page source for just this login form. So, okay, it's HTML. It's got some additional information in it, a lot of stuff in the head. You've got a title for it. You've got specifications for CSS. You've got the session ID. You've got some specifications for JavaScript. You've got a bunch of other stuff in here, more session ID, more script specification. Anyway, I could keep torturing you with this page source, but just believe me when I say there's a lot of text to wade through there. But embedded within all of that text is what is important, and very similar to the simple HTML form. There is a post method form with a username field and a password field and a submit button. So, so my thought was that, yeah, let's use curl to submit these forms and test the web browser interface. So the job submit details for the web browser interface, there's a lot more steps and going back and forth than there are for the one-shot REST interface. So what happens is we're going to log in with our username and password. We're going to save the cookies so that we can present those back in all the subsequent interactions we do with the browser interface. We need to upload our input zip archive, and we need to specify a label for that data item so we can find it in a list when we have to go through a form to select that input later. So we need to create a task, which is basically a job. And then we need to save the token associated with the start of this chain of events so that we can reference it as we go through each of the following steps. So with this task we've just created, we need to start the data item selection because we want to tie a specific input to this task. And we're going to find the data ID by asking the web browser interface to give us a list of all data items. And then whichever data item has our label that we used before, we're going to use that to find the data ID. And then we're going to set that data item ID to be used as input with the created task. And then we're going to set all the other usual parameters for an NSG job, like which tool to use on the back end. And then what parameters for the job, like nodes, cores, runtime, that kind of thing. Then we're going to do our final post request to save and run this task. And we're going to use the task label specific to this task so we can track it later. So once we've done that, we can query the job state by requesting the task list, finding the task by ID with the label that we've used before, and then we can get the state for that job. So we can monitor it every so often until it goes into submitted state, and then very similar to the REST monitoring script, we will notify that there's been a successful submit for the web portal interface, and then we will save this task info so that we can query the state of the job later, because again, there's a batch system delay for when the job starts running and when it gets completed. So here's the stored job info. So this is a Python pickle, not really meant to be human readable, but you can see that there are a few bits of text that say Jones dash, and there's a timestamp there. And those are the data item label and the task item label. So we've stored the job information. So later on, we can work on output verification. So again, we're going to have to log in with our username and password. We're going to save the cookies for use during this interaction. Then for any saved jobs, we're going to check status. If any of those happen to have been completed, we're going to retrieve the output and then compare the output file to a reference file and send appropriate success or failure when we verified or failed to verify. And then we're going to do some cleanup in the working directory. So the uploaded data item, the working directory where we've untarred our zip file and done the file comparison, those need to get cleaned out ideally. So while I was putting this talk together, I noticed that some of that is not quite working. I've got some garbage left over from old tasks, so I'm gonna need to go back and see what's going on there. So that's basically it for the testing. The bottom line is testing through the REST interface. It's pretty straightforward. If you want to do any sort of REST interface web programming, it's not that big a deal. The message for the browser interface is that it's possible. That's the important thing. You can do it, especially with this Workbench Framework code, because none of the job submission or the data movement requires JavaScript engine on the client side. So even though there's JavaScript code used in various pieces of Workbench Framework, you can do all of the necessary things without doing the JavaScript engine headless run of the code. So that's pretty nice for testing. If you want more information on the Workbench Framework code, there's a write-up at this URL off of philo.org. And then my email address is Kenneth@SDSC. If you've got any questions about this, I'd be happy to let you know what's going on. And I guess that's it. You guys have any questions?
Great, thank you, Kenneth. Very interesting. We do have one question here. So Chunhan, do you want to go ahead and ask your question?
Yeah, hi, Kenneth. Just simple, your browser interface is using REST interface and on the backend?
No, I mean these are two separate web servers.
Oh, okay.
One we use REST for, and the other we just use the web pages.
So, you are saying REST interface also like another standalone function, right, for the job management, you are saying?
Exactly, yes.
Oh, okay, got okay. Both are right now different. Okay, I got it. Thanks, Kenneth.
All right, sure.
Yeah.
Hey, thank you, Chunhan. Do we have any other questions? All right, we were at just about at the top of the hour. Thank you so much to both of our speakers. Really valuable talks. Kenneth, for myself, this was the first time that I think I really understood how a REST interface works. So it's nice getting that peek under the hood. And I could imagine the pushback that you got when you suggested just getting rid of the web page and doing everything through REST. But very interesting. Any last questions before we go? All right, thank you so much. And these slides and recording will be available on the ECSS Symposium page, and hope to see you all in June. All right, thank you.
Thanks, Bob.